Here we examine what the buoyant force is and how it arises from the vertical variation in pressure in a fluid. So in this picture, we've got a z-axis marked out in meters, and we're showing in this air here the gradual increase in pressure as we head towards the ground by about a 10,000th of an atmosphere per meter. Here is a red balloon, and for the sake of argument, let's say it's a cube-shaped balloon here. And the balloon is being pushed on all sides by forces arising from the pressure of the surrounding air. Now, the horizontal forces will cancel out by symmetry, so we'll just need to concern ourselves with the vertical forces on the balloon. So here's an FBD for the balloon showing 3 relevant vertical forces. First, there's the force of gravity on the balloon, since the gas inside is made of atoms, and atoms have mass, so there is a weight to the balloon itself. There's our little force of gravity on the balloon pulling down. That is likely to be small compared to the large pressure forces, pressure from the air below pushing up on the balloon, and then the pressure from the air above pushing down on the balloon. So I've called those FP2 for the pressure force at an altitude of 2 meters, and then FP3 for the pressure force pushing down from an altitude of 3 meters. Okay, some dimensions here. Let's call the height of the balloon h. That'll be 1 meter in this picture, and capital A will be the area of the top and bottom surfaces of our cube. So the net force in the z direction on our balloon will be given by the difference between those two pressure forces. That'll be a net force that is upwards minus the weight of the balloon downwards. And the difference between those two pressure forces, that is what we call the buoyant force. The difference between the pressure force, difference between the vertical pressure forces. So we're sort of combining these two forces into a single entity that we'll call the buoyant force. So each pressure force is the pressure at that location times the cross-sectional area of the surface of the balloon that's acting on. So there's a P2A pushing upwards on this surface minus P3A pushing downwards on that surface. Let's simplify this expression a bit. Since the top and bottom of the balloon have the same cross-sectional area A, same surface area A, we'll pull that out, and we get here the difference between pressures above and below the balloon. And from our principles of hydrostatic equilibrium, we know that the difference in pressure over a certain height in a fluid is related to the density of the fluid and little g via this expression. So let's replace that difference between pressures above and below the balloon with the density of the surrounding fluid, the air, times g times h, the height of the balloon. Let's then put together the height of the balloon and the area of the face. Those two terms put together here, recognizing that then that represents the volume of our balloon. The height times the area of one surface. So that's the volume of our balloon, getting us to this expression here. So the volume of the object, VO, we'll call it. And the volume of the object, our balloon, that will be equal to the volume of the fluid displaced, the volume of the air that would be there if the balloon weren't there taking up space. So we replace the volume of the balloon with the volume of the fluid displaced. And this expression here in this solid red box, this will be the expression we use most often as our starting point for a buoyant force. The force of buoyancy on some object is given by the density of the fluid displaced times the volume of the fluid displaced times little g. And that's guaranteed to be an upward force since the pressure below will be greater than the pressure above. Continuing on, this expression here, the density of the fluid times the volume of the fluid displaced, that's identical to the mass of the fluid displaced. And so we see we've arrived here at a proof of Archimedes' principle. This then, the mass of the fluid displaced times little g, that is exactly the weight of the fluid displaced as Archimedes claimed here. And so we will take this argument a bit further and look at what happens when you compare the weight of the fluid displaced to the weight of the object doing the displacing. So maybe go back to this line here, and we're going to manipulate this expression a bit more. So the net force on our balloon is then equal to the weight of the fluid displaced, that's our buoyant force pushing upwards, minus the weight of the object itself. Now let's replace each mass with density times volume. So the mass of the fluid displaced is the density of the fluid displaced, that's the surrounding air, times the volume of the fluid displaced. The mass of the object would be the density of the object, or the mean density of the object, times the volume of the object. And since we know the volume of the object is identical to the volume of the fluid displaced, we can factor those out and factor little g out to get to here, to see that the net force on the object depends on the densities of the object and the surrounding fluid. And we compare densities to determine the relative buoyancy. That is, three possibilities arise here. One, if the density of the object is less than the density of the fluid, then our net force in the z direction will be positive, as in upwards, as in we will accelerate upwards. We call that positive buoyancy, and this is what a balloon will do. If that is a balloon that is floating upwards, it does so because its mean density is less than the density of the surrounding air. Second possibility is that the two densities are equal, in which case the net force in the z direction is zero and its acceleration is zero. We call that neutral buoyancy. The object will accelerate neither upwards nor downwards, but will just sort of stay put, suspended in the fluid in a state of equilibrium, neutral buoyancy. If the density of the object is greater than the density of the fluid, then our net force here will be downwards. This net force will be negative here, so downwards. Our acceleration will be downwards. We call that negative buoyancy, and the object will sink. That would include pretty much any solid body that you put into air. When you just drop your pencil and it falls down, there is a force of buoyancy on that pencil, but we don't notice it because it is small compared to the force of gravity. That is, the density of the pencil is much greater than the density of the surrounding air, so we barely even notice that buoyancy is acting on it, but it is.